otherwise. So you see the regularity in the title of the talk, which tells you that regularity is actually important in this talk, which is why I'm going to assume everything is smooth so that we actually see the phenomena about regularity. So one form on W is a Liouville form if d alpha is a symplectic structure, meaning that d alpha of h d alpha is a positive volume form on W. And a dynamical this non-degeneracy of d alpha gives us some sort of correspondence between one forms and vector fields on the manifold, and that means that there is also a vector field corresponding to alpha under this correspondence, and I call that a Liouville vector field. This is going to give me a dynamical perspective into the theory. And an immediate consequence of the Stokes theorem tells us that whenever we have such a structure, the boundary of W needs to be non-empty. And for whenever we have we're talking about manifolds with boundary and we have a theory about them, it's important to have some reasonable boundary assumption. And to understand what is the reasonable boundary assumption here, we know that by Cartan's formula, this Liouville vector field expands the symplectic structure, which means that it's expanding the symplectic volume form. So you can think of this Liouville vector field as a vector field with positive divergence. And that means that it's essentially reasonable to think of this W flowing outward on the boundary of this four manifold, and whenever we have this condition, we call this pair of W and this one form a Liouville domain. The geometric interpretation of this boundary condition can be seen as follows. That means that if I restrict this one form to the boundary, which is a three manifold, then for this one form alpha of HD alpha on this boundary is going to be a positive volume form of the boundary, which means that alpha is a positive contact form. So that's going to be the geometric interpretation. So it's reasonable, given this dynamical perspective, it's reasonable to put some assumptions on this dynamics and try to see the consequences. And the Weinstein dichotomy is basically based on some sort of a dynamical assumption. More precisely, when I assume this vector field is gradient-like, which I'm not going to give you the detailed definition, but that essentially means that I have something like a Morse function, and this vector field behaves like the gradient vector field for this function. And the result is that I can do, what I do whenever I have a Morse function, which is Morse theory, and eventually I will have some sort of Handel decomposition kind of theory for these objects if I assume this extra condition on the dynamics of the Liouville vector field. And the result of this, one of the results of this kind of topological theory in this case is that the manifold should have this four manifold should have the topological type of at most half dimensions, which in this case is 2. And an immediate corollary of that would be that W needs to have a connected boundary. Another way of saying this is it's natural to describe the same thing in terms of the skeleton of this Liouville vector field, which is essentially the points of W, which don't flow out of the manifold under this the flow of the Liouville vector field. And the skeleton in this case would be the same as the Morse skeleton, which is just some CW complex with 0, 1, and 2 cells. And any Liouville domain with this property is called Weinstein. And when I say that, I mean up to homotopy, because most of the consequences that we draw about the symplectic topology in this case is, doesn't depend on homotopy of the Liouville flow. So whenever I have a Liouville form which can be homotoped to satisfy this condition, I call that a Weinstein. Very basic example can be described on the disk, and this one form, okay, think of the four-dimensional disk equipped with the coordinates x1, y1, x2 and y2, and we can define this one form that I have over there. And if you think of the Liouville vector field, it's going to be some sort of radial kind of vector field on each of these xy, like coordinates. And obviously we see that it's also flowing out of this four manifold, which means that it's automatically Weinstein. This example can be generalized to when we have to the disk bundle, the cotangent unit cotangent bundle, disk bundle, and other examples can be constructed by using like attaching handles, and also it is well known that this Weinstein geometry has very close relation to Stein manifolds, and in particular that gives us a lot of new examples, as well as the fact that there's a very close relation between the Weinstein case and complex geometry. So in some sense, we can think of the Weinstein case as the kind of case of like Liouville geometry, where in many ways you have the symplectic structure is resembling some sort of complex structure. So on the other hand, the theory about the Weinstein case is very, very much developed in many ways. And on the other hand, the non-Weinstein case is left more or less unexplored. We know very little about the non-Weinstein Liouville geometry. Even some kind of basic questions are not answered yet. The most basic question would be, do we have examples of non-Weinstein Liouville geometry? That was actually open problem for a while, but eventually the first examples were provided by MacDuff in 91, and then Geigis and Mitsumatsu built on those kind of ideas. And these ideas were probably most generalized in the work of Mitsumatsu, where he showed that if I have a three manifold and admitting an Anosov flow, which is some sort of dynamics, then there is, if I consider the interval across that three manifold, I'm going to get a like four manifold with boundary, and Mitsumatsu showed that we can use this the dynamics of an Anosov flow to construct some Liouville form on this four manifold satisfying this boundary condition. And this example is automatically Weinstein. Essentially, like schematically, this is the picture I have because I have this interval across M. And what you see is that the topological type of this four manifold is three-dimensional, which means that there's no way I can deform this Liouville form to make it Weinstein. And we see that manifested in the fact that this manifold has disconnected boundary. So there's some sort of topological obstruction that tells me that there's no way that these examples can be Weinstein. So this is kind of rough introduction to non-Weinstein Liouville geometry. For the rest of this talk, I'm going to start with some rough introduction of Anosov flows as well. Then I will discuss Mitsumatsu's construction and how it is some sort of basis for a Liouville geometric theory of Anosov flows. And after that, I will try to convince you that some deep phenomena from the regularity and rigidity theory of Anosov flows are somehow inherited in the geometry of the resulting Liouville domains. That is represented in a dynamical rigidity phenomena as well as geometric rigidity phenomena. And eventually, I will discuss that actually these Mitsumatsu's examples are, in some sense, characterized non-Weinstein Liouville geometry under some natural assumptions. So it's not just some coincidence that there is some interplay between hyperbolic dynamics and kind of Liouville geometry just because we have these examples. There is something kind of deeper going on, in my belief. Okay. So a very rough introduction to Anosov flows. So I'm going to talk about Anosov flows in dimension 3. So let M be a closed-oriented connected three manifold, and X is going to be a vector field. And I use this superscript T to show that I'm talking about the flow generated by X. Anosov flows are kind of classical examples of chaotic dynamical systems. They are known to have very subtle rigidity and regularity theory aspects. And it's also well known that they have deep connections to geometry and topology. So the definition is as follows. So I have a X is an Anosov flow. If I have a continuous splitting of my tangent bundle into 3 line bundles, one of them is going to be the direction of the flow X. And in these 2 other bundles, if I look at one of them, let's say, denoting them by EU and ES, and on one of these line bundles, the action of the flow expands the lengths of vectors exponentially, and on the other one, the action of the flow contracts the lengths of vectors exponentially. If I want to draw a schematic picture, it's kind of the a standard picture of any hyperbolic behavior. And you see here that the action of the flow is kind of represented in this picture by dilation in the EU direction and a contraction in the ES direction. And these line bundles are called like a stable and unstable, directions or line bundles of this flow. Examples, the 2 kind of standard examples are as follows. We can construct them by suspension. So for instance, if I have an area preserving hyperbolic diffeomorphism of the torus, which is going to be an element of SL2Z with real eigenvalues, I can use this map to look at the torus cross interval and use this map to glue the 2 boundary components, and we can get a torus bundle. But what we also get is that we can get a suspension flow that we get from this map. And if this the map we started with was a like hyperbolic diffeomorphism, we're going to end up with an Anosov flow. In this case, we call this suspension flows. And the other important examples, they come as geodesic flows, which means that whenever I have a hyperbolic surface, if I look at the geodesic flow restricted to the unit tangent space, which is a 3-manifold, the hyperbolicity of the metric is now translated into the anosovity of this of the geodesic flow, on this 3-manifold. For about like 20 years or so, these were actually the only examples known in dimension 3, but thanks to many kind of different various surgery kind of constructions, now we know that we have many more examples, including hyperbolic manifolds and so on. The connection to geometry and topology is mainly based on the use of foliation theory in the study of Anosov flows, and that's based on the following facts. If we take any of these 2 line bundles, ES or EU, the stable or unstable ones, and if we pair them with the direction of the flow, we're going to get 2 plane fields. And these 2 plane fields are going to be invariant under the flow, and this invariance is then translated into the basically integrability of these plane fields, which means that they are going to be tangent to foliations. We have more than integrability, we have actually unique integrability. So they're going to be tangent to foliations, which means that if I really want to have a more honest picture of these flows, I should think of any flow segment living on the intersection of a pair of foliations. And on one of these foliations, the nearby flow lines are kind of being sucked into the center flow line, and the other one, the kind of nearby flow lines are running away. One thing that we should notice here is that even though this is some sort of a local picture, there are kind of a few things you should have in mind if you want to interpret this as a local picture. One of the things is that this is a low regularity picture. So the splitting that I had was just continuous in general, but Anosov himself showed that they are actually Holder continuous. But even when the flow is smooth, I don't have much regularity for this splitting, and that also includes these plane fields. And the other thing is that these kind of invariant bundles are determined by the long-term behavior of the flow, which means that if I perturb my flow in a neighborhood, that's gonna kind of mess up all these foliations in my entire manifold. So in some sense, it's a little bit tricky to interpret this as a local picture. In particular, about the regularity, these are only a priori holder continuous, but it is well known that in this kind of dimension 3 and in this setting, these plane fields, the weak bundles, the invariant plane fields are actually C1. And that was shown, I think, by different people, but my main source is Hirsch-Pugh-Schub. And later on, Hasselblad refined these kind of statements by finding actually like lower bounds for the Holder exponents of these derivatives of flow. So we can tell more about what is this exponent. And something that you should kind of notice is that Gis has showed that we have C2 if and only if this flow we have in the classical examples. So except the classical examples, we actually know that it's actually never C2. These plane fields are never C2 except in the classical example. So we need to be able to deal with these regularity kind of restrictions and so on. And there's something kind of subtle going on about the regularity. Also, this splitting is not necessarily orientable, but for the sake of this talk, I'm going to assume these line bundles are orientable, which can be achieved by going to a double cover. So based on some observations of Mitsumatsu and Eliashberg-Thurston, a local contact geometric model can be kind of described for these Anosov flows, which is, at least philosophically speaking, it has higher regularity. It is truly local, and it, in some sense, reflects the stability features of Anosov flows a little bit better. And, that is actually based on this, related to this Mitsumatsu examples of Liouville domains that I mentioned in the beginning. So recall that I call a one form alpha a contact form on a 3 manifold if alpha of HD alpha is a volume form. If it's positive, a volume form, I call it a positive contact form, otherwise a negative one. Standard examples can be easily written down for R3. And in the picture, we can keep track of the kernel of this one form, which we call a contact structure, or maybe a coorientable contact structure to be more precise. And here we see this rotation, which manifests the non-integrability of this plane field. So contact structures, as you know, are the kind of, in some sense, extreme opposite of foliations. And we have the Darboux theorem that tells you that this is actually an honest picture locally. So in some sense, we can think of contact structures as rotating plane fields to be a little bit naive. The main observation of Mitsumatsu and Eliashberg-Thurston in the mid-90s, which is the basis for this contact geometric theory of Anosov flows, is pretty kind of elementary observation, but I consider it as a very deep observation. So, and it tells you the following. It says that if I have an Anosov flow, I had this schematic picture, which is describing the action of this flow on the tangent bundle. If I look at the bisectors of these two invariant plane fields, I'm going to get two other plane fields. And the action of the flow is actually inducing some sort of rotation on these two plane fields. And if you keep track of the orientation conventions, you can probably convince yourself that one of these two plane fields is going to be a positive contact structure and the other one is going to be a negative contact structure, which means that any Anosov flow is lying in the intersection of a pair of transverse positive and negative contact structures. That was the observation of Eliashberg and Eliashberg-Thurston and Mitsumatsu in the mid-90s. And we call such a pair of contact structures a bicontact structure supporting this underlying flow. Now, you might, if you're very optimistic, you might want to hope that maybe this bicontact condition describes Anosov flows, kind of characterizes them. But it turns out that these bicontact structures are much more abundant and much less rigid than Anosov flows. But it turns out that they have some interesting dynamical interpretation. And the dynamical interpretation is as follows. So suppose that you have a pair of positive and negative contact structures, and you can still have this, think of the fact that the flow in in the intersection, the vector field that you take in the intersection is going to induce this kind of action on these two plane fields, and with some sort of contraction argument, you can convince yourself that there's going to be an invariant plane field in the middle. And also, if you go backwards, there's for similar argument, we'll give you another invariant plane field here. So having these two bicontact structures, first of all, it does give you a pair of invariant plane fields, which one of them I'm going to call E, the other one I'm going to call F. But actually, it's going to give you something more. So if you think about this angle, use some metric on the tangent space. And if you think of this angle, the rotation that you see tells you that the action of the flow is increasing this angle. And when the angle is increasing, that means that the tangent of the angle is increasing, which means that the ratio of this y over x, this ratio is increasing. So that is going to be manifested in the next definition, which means that, okay, whenever I have a bicontact structure, first of all, I have two invariant plane fields, which is just, you can describe it as a splitting of the normal bundle of the direction of the flow. And the ratio of these two, like the ratio of the lengths are increasing, which is like this angle kind of increasing. And we call a flow with this condition a projectively Anosov. We can think this is a generalization of Anosov flows, and we can think of this as a weak notion of hyperbolicity, which is bridges hyperbolic dynamics and contact geometry. And sometimes they also call this a dominated splitting, and they say that this kind of bundle F is in some sense dominating E. I don't know, sometimes they write it like that. So we have a dominating behavior. We have a splitting of a plane field. We have two invariant plane fields, and the flow line, one of them is in some sense dominating the other one. And rephrasing the observation of Mitsumatsu and Eliashberg Thurston tells you that we have an if and only if kind of situation, meaning that you have a flow is projectively Anosov. If and only if I have this bicontact structure. Okay. To understand the connection to Liouville geometry, the construction of Mitsumatsu of these non-Weinstein examples helps us go from this general case of projectively Anosov to an Anosov case. So to see this, we should consider a linear interpolation. We can consider a linear interpolation of two contact forms. So suppose I have this bicontact structure. And I take, let's say, two, contact forms for my contact structure. And I look at the linear interpolation of these two on these four manifolds, four manifold W, which is just the interval. S is the parameter for my interval, across M, which is a four manifold. So now I have a one form on this four manifold. And if I think of this interpolation, there is some moment for any point where this interpolation is passing through one of these two invariant bundles, right? In the four-dimensional picture, at any point, again, there is some, there's some time that I'm passing through this invariant bundle, and that gives me some graph inside my four manifold. And now, so this is kind of the graph that I get. That is, whenever the kernel of this one form matches one of these invariant bundles. And if I check the Liouville condition of alpha in this one form in general, it is going to be translated into the lead derivative of alpha in the direction of the interval direction, and the Anosov flow direction to be linearly independent. And if I specifically look at this Liouville condition on this graph, at this moment I'm passing through the invariant bundle, this condition will be reduced to something of this form, which is the lead derivative of alpha u, where alpha u is just the restriction of my one form to this, to this graph, times alpha plus minus alpha minus. And this alpha plus minus alpha minus is going to be non-vanishing on the kernel of this alpha u, which is my invariant bundle. And here, if you look at this, oops. If you look at this lead derivative of alpha u showing up here, so my Anosov flow preserves the invariant bundle. So this lead derivative is going to be it's going to have the same, so Anosov flow is preserving the kernel of this one form, right? So the result would be just a multiple of alpha u again, and this multiple, which is a function in general, is going to show you how much dilation you have in the normal direction of this plane field, which is going to be in the EU direction, right? So I'm looking at when I'm passing through this, and I'm measuring the expansion of this measure induced from alpha u in the unstable direction. And essentially, this means that the Liouville condition is going to be the Liouville condition on this graph is going to be actually equivalent to the absolute expansion of the norm induced from my Liouville form on this unstable bundle. Mitsumatsu essentially showed the other way around. Mitsumatsu showed that when I have an Anosov flow, I can always start from this kind of expanding measure and perturb it into two contact structures, basically supporting the Anosov flow. But the way I describe it right now shows you that there is some sort of one if and only if situation going on. So you have the Liouville condition if and only if we have an expansion. So we call a pair like this a Liouville pair, or since I describe it as a linear interpolation, a linear Liouville pair, which is why I'm putting this superscript L here. So as I mentioned, this Mitsumatsu construction gives you some sort of if and only if situation. And now I can describe Anosov flows purely in terms of these Liouville conditions, because I had a Liouville condition guaranteeing the expansion of the sum norm in the unstable direction. And similarly, I can describe the contraction of the stable bundle using another Liouville condition. In other words, I have a flow being Anosov if and only if I have a pair of positive and negative contacts, a bi-contact structure. As I mentioned, this automatically gives me a pair of invariant plane fields. And now I also have some sort of domination relation. I have a relative expansion in the direction of F versus E, but I can guarantee that this expansion is a kind of absolute if I have some sort of Liouville condition. And similarly, so this is one way of interpolating between these two plane fields. Also, I have another way of interpolating between these two plane fields. And if I look at the Liouville condition in this other interpolation, I'm going to have I'm going to guarantee the existence of a norm which is absolutely contracting on the stable bundle. So I'm not going to write down the precise, kind of description, like a formulation of the theorem, but you see that I can guarantee anosovity using the bicontact condition and two different Liouville conditions. And the fun thing about this kind of model is that it can be taken to be as regular as the flow. It doesn't have the low regularity situation of the, the foliation theory. Then obvious question that you might want to ask me is that, okay, what if I only have one of these Liouville conditions? What does that mean, right? So whenever I have one of these Liouville conditions, in some sense, I'm satisfying half of the conditions of an Anosov flow, and I call this partially hyperbolic, which means that I do have these two invariant bundles, but my kind of dominating invariant plane field is actually does have this expansion, absolute expansion, but the dominated plane field, it might be expanding or contracting, but it's anyways dominated by F. And whenever I have, in terms of this Liouville condition, again, that this can be described by having these two, having a bicontact structure and only one of the Liouville conditions, one Liouville pair. And it's an important and interesting, intermediate between general projectively Anosov and Anosov flows. And you see that Mitsumatsu's construction still works in this generality. And, I'm not gonna maybe like go into too much details. I'm trying to center my talk more about Anosov flows, but actually it does affect the theory of this non-Weinstein geometry as well. There is some subtleties when we go from Anosov case to the more general case. There are some kind of more exotic behavior that you might be able to see in this case. Examples of these partially hyperbolic flows, they can be constructed using the dA deformation, which was first introduced by Smale, I think. And that means that whenever I have, let's say, a periodic orbit, I can just add some, radial expansion to this and make the the unstable direction very much more expanding, and eventually have make the stable bundle also go backwards and be expanding. So it's not hard to deform an Anosov flow to a partially hyperbolic flow. And but as far as I know, it's not really understood. It's not known whether we have other constructions as well. So this is the only way that I know we can construct partially hyperbolic flows. But still, the nice thing is that Mitsumatsu's construction still works for this class. And something that I would like to mention is that, these invariant plane fields in the partially hyperbolic case, they're not necessarily C1 anymore. And as it was shown by Eliashberg Thurston, they're not actually even uniquely integrable anymore. So you might have actually branching foliations in this case. So we actually lose the nice regularity theoretic aspects as well. Okay. So now I'm going to switch gear and tell you that more about how deeper phenomena about the regularity and persistence and things, rigidity of Anosov dynamics, or more generally hyperbolic dynamics, is inherited in this Liouville non-Weinstein Liouville geometry that we just constructed. So before anything, I should say that I need to switch to some more generalized framework. And for the deformation purposes, I'm going to consider a non-compact framework, which is called like Liouville manifolds. And the idea here is that of this generalization is that everything, all the aspects of Liouville geometry is encoded in the interpolation of these plane fields. And every other information is kind of extra. And when I say that, that means that up to strict Liouville equivalence, not even up to Liouville homotopy. So to have this generalized interpolation kind of framework, we are going to consider this R cross M now. And we are going to consider any kind of linear kind of combinations of these two contact forms. So again, suppose I have these two bicontact structure, these two contact structures. I take two one forms for these two, and I look at this linear interpolation of these two contact forms using these positive functions that I'm using lambda minus and lambda plus. Something that you should notice here is that I'm taking these functions to be from they can even depend on the point. In the previous example, they were just 1 minus s and 1 plus s, right? It didn't depend on the functions I was using for interpolation. They didn't depend on the point, and they only depended on this parameter s. But now I'm even allowing the interpolation to be different point-wise. And it's not really hard to notice that if let's factor out this lambda minus. So this is the kernel is going to look like this. It's the same as the kernel of this kind of other one form. And that means that the interpolation of the plane fields that would be equivalent to this function showing up here being increasing or decreasing depending on your convention. So the interpolation condition of the plane fields is equivalent to assuming that the ratio of these two, these two functions, is increasing if I move in the direction of s. Again, that can be different point-wise, but all I need is the partial derivative in the direction of S to be increasing. And I'm going to add the right infinity assumptions to guarantee the completeness of these Liouville forms, which is not really that hard to kind of enforce. And whenever I have this information, I call that a Liouville interpolation system. And if you don't want to think about that, it's great, because it is important to have a generalized framework for many reasons. And there is we have the linear interpolation in the in the compact case I mentioned. We also have exponential model, which is used in different parts of the literature to consider whenever Liouville manifolds are necessary. As you know, it's more convenient to define these invariants when we have complete Liouville flows. And the importance of having a generalized framework is that there is some technicalities about the low regularity nature of the setting. And that means that anytime we want to change the interpolation regime, we will need to go through these technicalities again and again. Right now, I have like two different projects that I'm using two different other kinds of like interpolation, and I don't want to go through all those technicalities again and again, which is why a generalized framework is actually necessary. But for the purpose of this talk, if you don't want to think about these functions, you can simply think about this exponential kind of model, or an exponential Liouville pair. So, just think of lambda minus lambda plus as e to the power of minus s and e to the power of s, if you're more comfortable with that. And this way, Massoni a few years ago showed that, similar phenomena, theorems that we had about the Mitsumatsu construction holds in this case, and we can show that these ideas can be extended to the case of these Liouville interpolation systems. And most importantly, Massoni showed that the space of such objects is homotopy equivalent to the space of Anosov flows, which means that you can use them in order to answer questions of study questions about the classification results questions in Anosov dynamics. And in particular, they introduced in a joint work with Chelebek, Lazarev, and Moreno. They showed that they can define new flow theoretic invariants for Anosov flows using this setting. So to move towards this dynamical rigidity phenomena, I want you to pay attention to some special foliation that we have in this setting. So whenever you pair the direction of the flow and this interval direction, we get a plane field, and it's going to be tangent to a trivial exact foliation, meaning that exact Lagrangian foliation, meaning that the restriction of my Liouville form to this plane field is vanishing completely. We call these weak normal foliations. They're going to weak normal plane fields, and they're going to be invariant under the Liouville flow. And we can also see that the Liouville direction y, so y here is the Liouville vector field, is going to be transverse to the interval direction, which is actually, if you pay more attention, this is actually equivalent to this interpolation of the plane fields. And also we can see that the y direction is entirely the Liouville flow is always going to be sitting inside this plane field. So the Liouville flow is the Liouville vector field is always a linear combination of this interval direction and the Anosov flow direction. So for the sake of less complication, I'm going to state this for Anosov flows and not partially hyperbolic flows. As I mentioned, we can have this kind of Liouville interpolation systems for partially hyperbolic flows, but there is more subtleties to that. Let's state this for in the Anosov case, and suppose I have one of these interpolation kind of Liouville cases. And this theorem is supposed to convince you that there is some sort of rigidity in the Liouville dynamics, or the dynamics of the Liouville flow. The first thing that we should notice is that the skeleton of this Liouville flow is exactly the graph that I described before, which is going to be the graph that we get as the time, pointwise time passing through this invariant bundle. A very nice consequence of this is that this graph is exactly as regular as this invariant plane field, which is going to have some consequences, as I mentioned. And in particular, since I'm assuming Anosov, this graph is always at least C1, but in a non-trivial case, borrowing from the theory of Anosov dynamics, as I mentioned, for partially hyperbolic case, we know that it can't be, sometimes it's not necessarily C1. So in the partially hyperbolic case, we get graphs that are guaranteed to be C0, but not C1. But let's stick to Anosov case. It's guaranteed that we have C1 skeletons. It's going to have some consequences. But if I look at the restriction of the flow, of the Liouville flow to this skeleton, which is a copy of my original 3 manifold, is going to be some special reparametrization of my Anosov flow. And this special parametrization is called the synchronization, because remember that, when I had this when I was trying to express the expansion of this norm in the unstable direction, I said that that can be described as a function, by saying that the lead derivative of this one form or this measure along the flow is a multiple of that one form. But we know that for Liouville flows, we always have this criteria, right? This is the condition for Liouville flows, which means that I need to reparameterize my flows so that this function showing up is equal to 1. And it's nice that this reparameterization is actually unique up to conjugacy. So I have some uniqueness of the skeleton dynamics up to, even if I reparameterize my flow, the skeleton dynamics is unique up to conjugacy. And I also have normal repellence in the kind of normal direction of the skeleton. And it is well known that this normal repellence or this normal hyperbolicity of this invariant kind of graph is going to result in the C1 persistence of the skeleton, which means that if I perturb my Liouville dynamics in a C1 way, so let's say I deform my Anosov flow in a C2 way, that deforms the Liouville form in a C2 way, and that deforms the Liouville, if I deform the Anosov flow in a C2 way, that's going to deform the Liouville form in a C2 way, which means that that's going to deform the Liouville vector field in a C1 way, and that is enough to guarantee that the skeleton is going to be deformed in a C1 way. So we have some nice persistence coming from the normal repellence of the skeleton. We don't have this normal repellence, for instance, in the case of partially hyperbolic setting, which makes things a little bit more exotic. And a corollary of this is that the Liouville flow is actually unique up to C1 conjugacy, independent of all the choices that I made, all the contact form, contact structure, the interpolation, functions, and even the reparameterization of the flow. They're not going to affect the Liouville flow up to, like a C1 conjugacy. So we see some rigidity here. And some nice consequence of this, some corollary, some for me surprising corollary of the previous theorem is based on the fact that, as I mentioned, this graph is exactly as regular as that plane field, that invariant plane field. And that means that we can use Liouville geometry to translate the question about the regularity of the plane field to the regularity of the graph, which is a much more classical and easier problem. As a consequence, we can recover the lower bounds of Hasselblad, which with much more easier technology. Liouville geometry reduces the question of regularity of these plane fields into a much easier question. We can recover the lower bounds of Hasselblad for Anosov flows. We can extend the lower bounds of Hasselblad to partially hyperbolic case, which is, the techniques of Hasselblad does not give you that, but we can actually extend and generalize the result of Hasselblad. And we can even get a parametric version of Hasselblad's lower bounds based on this basic persistence theory of this graph. In the Anosov case, that will be translated into the fact that the weak invariant plane fields C1 depend on the C2 deformations of the Anosov flow, which is something that it was not known in the literature before. So we can use Liouville geometry to say something about the regularity theory of Anosov flows, which goes beyond what we had in the literature before. So now it's time for geometric rigidity. So since we have this, as you know, using the Moser technique, we can assume that under these Liouville deformations, we can assume that the symplectic structure, d alpha, is constant after some isotopy. And since this Liouville flow, this Liouville vector field and Liouville form are they correspond to each other on this correspondence. In some sense, the rigidity that we see for the dynamics, there should be some manifestation in the rigidity of the Liouville form, which I call geometric rigidity. To notice this, so first remember that the Liouville vector field is included in this kind of exact Lagrangian, trivially exact Lagrangian foliation. And we observe that if, let's say, this Liouville vector field is a linear combination of x and the interval direction, that can be, we can go back and forth, and we also have a basis for the Liouville form, even under the deformations. And this basis is going to be the Lie derivative of alpha in the direction of s and the Lie derivative of alpha in the interval direction. And that essentially means that the Moser technique works better than usual if we fix the flow direction x. So suppose I'm fixing my Anosov flow, and any deformation I do, which corresponds to making different choices for these contact forms, the interpolation functions, and so on. As long as I fix this Anosov flow, I'm restricting to a special class of deformations, which are all of them are vanishing on this exact Lagrangian foliation that kills some of the degrees of freedom I have, and eventually I can get use the Moser technique in this setting to recover the Liouville form strictly, and not just up to homotopy, which is the standard consequence of the Moser technique. As a result, we get you can kind of transcend the Mitsumatsu's construction into some sort of one-to-one correspondence between Anosov flows, or more generally partially hyperbolic flows, up to conjugacy, and strict Liouville equivalence between Liouville forms induced from this interpolation regime. And so we get not only initially we had a construction, we transcended to some sort of characterization of Anosov flows, and now we go one step higher and have a one-to-one correspondence between appropriate classes of dynamics in dimension 3 and strict Liouville equivalence classes in four-dimensional Liouville geometry. And a nice corollary of this is that we can improve the uniqueness of the Liouville flow that we had, because Moser technique is now, boosting the whole kind of regularity thing. Because if everything was smooth, I can use the kind of Moser technique in a smooth way, which means that the Liouville flow is not, previously I said that was unique up to C1 conjugacy because the graph was C1. So if I wanted to have some sort of, correspondence between two different Liouville flows, I needed to use, a priori, I needed to have just a C1 uniqueness. But actually, the corollary of the Moser technique is that the Liouville flow is actually unique up to smooth conjugacy. So we can even improve the regularity of the uniqueness of this Liouville flow, or the rigidity of the Liouville flow as well. And another corollary of this is that, previously I said that, okay, we had this linear interpolations, we had exponential interpolations, and it was kind of a confusing thing in the literature that, okay, what is the difference between these two? And I think it was most explicitly raised by Massoni a few years ago in his paper. But here the corollary is that the only thing difference between a a linear model and an exponential model is just compactness. And when I say that, I mean up to strict Liouville equivalence. That means that any supporting linear Liouville pair can be strictly embedded into any supporting exponential pair. So we have strong rigidity, and we actually resolve that kind of confusion as a corollary of this geometric rigidity as well. The final kind of discussion is that about the persistence of the skeleton. And in the final theorem of this talk, I want to mention that Mitsumatsu's examples are not only some nice examples where we see some deep interactions, uh, but also they characterize non-Weinstein Liouville geometry under some reasonable, natural assumptions. And before that, you should notice that this is a work of Monnier and Hirsch-Purshub that C1 persistence is equivalent to normal hyperbolicity. And I mentioned C1 persistence because I don't want to define normal hyperbolicity. C1 persistence, I think, is easier to grasp, kind of conceptually. And this is the theorem. So suppose we have a Liouville manifold and we have an oriented C1 persistence, which means that I have a C1 skeleton, but it also depends in a C1 way on this C1 deformations of the Liouville flow. A three-dimensional skeleton, which is guaranteeing that I'm in the non-Weinstein case, and this extra assumption that I want the kernel of my Liouville form to be transverse to the skeleton. That is something that we did have in the Mitsumatsu example. Then we can conclude that the Liouville vector field restricted to the skeleton is a synchronized Anosov vector field. Notice that I'm not mentioning partially hyperbolic because, as I mentioned, we don't have that normal repellence in the partially hyperbolic case. So we actually do have a synchronized Anosov flow on the skeleton with this kind of natural assumptions. And the Liouville manifold is a C1 strictly Liouville equivalent to the Mitsumatsu's examples, or like this Liouville interpolation system. And it's interesting, I think, that where this is not a when we have why we have a C1, what is non-generic in the Mitsumatsu's example? Why don't we have a C infinity, strictly Liouville equivalence here, right? This construction tells us that the only thing non-generic in the Mitsumatsu's example was the fact that these exact Lagrangian foliations were C infinity by construction. By construction, that interval direction and the Anosov flow direction, they were just C infinity. So those foliations were just C infinity by construction, but these are invariant foliations for Liouville flow. And if I just perturb the setting, they don't necessarily stay C infinity. And this C1, equivalence tells you that the only thing non-generic for in the Mitsumatsu's examples is the regularity of these exact Lagrangian foliations. Other than that, we have these are enough conditions to guarantee that we are in the Mitsumatsu's example. There is more subtlety if we go to the partially hyperbolic case. We might have, it's not known, we might have more exotic behavior for Liouville dynamics, and a priori we might have actually examples which are not equivalent to these Liouville interpolation systems. So there is something going on. Also, if we can drop the, let's say, this transversality condition, if we do that, we can still say something about the dynamics of the skeleton. In particular, it's guaranteed that it does have a hyperbolic invariant set. But I'm not going to mention that. We don't have examples of that, but we do understand what happens to the dynamics of the skeleton if we drop this, transversality condition. And the final corollary of this is that we have a one-to-one correspondence between positive reparametrization classes of Anosov flows up to conjugacy and Liouville forms on R cross that 3 manifold with C1 persistent 3-dimensional skeleton and transverse to the Liouville kernel of the Liouville form up to strict Liouville equivalence. And I think this one-to-one correspondence is actually much kind of more natural than the previous one, because in the previous one-to-one correspondence, I'm looking at Liouville forms induced from some Liouville interpolation system, which means that in some sense I'm fixing my product structure, right? So being induced from a Liouville interpolation system, for me, it's not as natural as the condition I'm describing in this other kind of one-to-one correspondence, which are purely intrinsic and coordinate-free conditions, about the persistence of the skeleton and transversality. Well, thank you so much for listening.
Thank you. Are there any questions?
May I ask a question? So there is a theme in Anosov dynamics and partially hyperbolic dynamics, topological abstractions on manifolds for which such flows exist. For instance, for partially hyperbolic diffeomorphism, there was a big work by Burago and Ivanov proving that on S3 there is no such gadget and so on. So can your techniques say something in this direction?
So we hope so. This was, based on the work of Massoni. I mean, he was the first to, mention this. And, the idea is that the space of these geometries is homotopy equivalent to the space of Anosov flows. So we should be able to, a priori, we hope that we can use these kind of classification or obstructions, as you mentioned, of the existence of these types of symplectic or Liouville structures to say something about the space of Anosov flows, in particular their existence, the obstructions, or like their classification. And there were kind of, and we showed that, they can be also extended to any kind of, the result of this work tells you that these kind of theorems work in much more generality, and there were invariants introduced by Chilebek, Lazarev, Massoni, Moreno, about coming from floor theory and Fukaya categories and things like that. But so far, our main kind of technical issue is that these are kind of hard to compute, and we haven't. There hasn't been enough. I mean, it's relatively new, so I'm hoping that changes. Maybe if you ask me in a couple of years, I hope to have a better answer, but we hope that these invariants coming from the floor theory can give us new obstructions, for instance, for the existence of these types of dynamics.
Thank you.
Mm-hmm.
No, okay. Any other questions?
Can you, Surena?
So yeah, you can talk. Julia has a question from here.
Yeah, can you do these for Surena flows, like when you have more singularities, when you have singularities of flows?
That's a great question. A singular version of this question is also not known. So there are different kinds of generalization. We can try to hope to go to some sort of, there are different theories for singular Anosov flows or singular kind of partially hyperbolic flows, and right now it's not clear what is the what is the right generalization to the singular setting. We don't know that yet. We also don't know much about like what happens in higher dimensions, for instance.
Thanks.
I think it's reasonable to expect that there is some notion of singular hyperbolic dynamics for which we can still have something like this, end up with some sort of singular hyperbolic dynamics on the skeleton. But right now, it's not clear to me. There are different notions. We have sectional hyperbolic, sectionally Anosov flows. We have singular partially hyperbolic flows, and we don't know what's the right notion.
Okay, so if there are no further questions, thank you again.